there is no new element. All the elements are from this particular given set. So this set is closed under multiplication defined by D-scale list table, and we note that first of all we note that 1 is identity with respect to the binary operation, which is multiplication in this case. So 1 is identity. Secondly, you can see the inverses. -1 is inverse of -1. Note that it is 1. So -1 is inverse of -1. Then it is 1. I is inverse of -I. This is 1 here. So -I is inverse of I. Then we have 1 here. J is inverse of -j. We got 1 here. So -j is inverse of j, and so on. So inverse of each element exists. You can see from the table. Inverses are evident. You can easily see what the inverses are. So having done that, number 3, you can check the associative law by trying different combinations. So you can check the associative law by inspection. In fact, you can check the associative law by inspection. It takes quite a lot of time, but it's not difficult. In fact, it's very easy thing. And then number 4, we note that I multiplied with j is equal to k. So ij is equal to k, and j multiplied with I is equal to minus k, and j multiplied with I is equal to minus k. So this particular group is a non-commutative group. So therefore, the Quaternion group is non-commutative group. Therefore, the Quaternion group is a non-commutative group. A non-abelian group, mostly we call it non-abelian. Is non-abelian group. So this was another example of non-abelian group. Now we come to another example of non-abelian group, and that is about bijections of a set onto itself. So let's come to this particular example. So another example, you know about bijections. If we are given a set, then one-to-one and onto mappings of that set onto itself is called bijection. One-to-one onto mappings of that set onto itself is called bijection. So if we like, we can take just an abstract set, but let's take a real set, that is set of real numbers, and take real valued real functions. So Another example of a non-commutative group. So another example of a non-commutative group. Example of a non-abelian group. Let's call it non-abelian. So, for example, we take the set of real numbers and we take all the bijections from set of real numbers onto itself. So, let's write it as a proposition. The set of all the bijective real valued real functions is a group. In fact, we can take bijective maps from a set onto itself. I have chosen set of real numbers because you are very familiar with real valued real functions, so it will be easier for you to understand this thing in this form. So let's prove it formally. Although it is very simple thing, so let have the proof. Let's denote the set of all real valued real functions by SR. If you want to take set A, then you can write it SA. Since we are taking set of real numbers, so we write it SR. So let SR is equal to F such that F is a function from set of real numbers onto itself is a bijection. Now you know what bijection means, one-to-one onto function. So let this be a bijection. We shall prove that SR is a group. So first of all, we have to define binding operation. So binding operation. So far, we are going to take composition as binding operation. So for any two bijective functions f and g belonging to SR, we define you know that if this is a function from R onto R, which is bijective, and this is another function from R onto R, this is again bijective, we can compose these two functions with each other and we get a bijective function from R onto R. We denote it by G circle F. This is slightly very careful thing because when we write functions, order is first is F and next is G, but when we write composition, we write G first and G compose. There is a reason for this. We may discuss this reason at some time, but for the time being, just note that we have to be very careful when we are talking about composition of functions. So anyway, for any two real valued real functions f and g, we define their composition and we know that G circle F is bijection as well. That is G circle F belongs to SR. So this composition gives us binding operation. Therefore, composition is binary operation in SR. So this is the binary operation. Secondly, we come to associativity, and you know that by composition of functions, in fact, from a set to itself is always associative. So we know that composition of real functions is, we know that we have taken valued real functions because we have a lot of experience of working on these functions from your courses on real analysis and calculus. So we know that otherwise we would have taken any abstract set. So we know that the composition of real valued, and you must be very familiar with this phrase, real valued real functions. So we know that the composition of real valued real functions is associative. In fact, this is in general. Therefore, in our particular case, therefore, if we take three functions, three bijections f, g, and h belonging to, we denoted it by SR, we have if we compose these H circle G circle F, this must be equal to H circle G circle F. So this is very simple rule from our previous experience. So composition of functions is associative. So associative law under composition holds in SR. So associative law. So associativity is there. So composition is a binary operation and composition is associative. So SR is associative under binary operation, composition of functions. Anyway, composition is the binary operation which is associative in SR. That's it. Now we come to third condition, and that is existence of identity. Existence of identity, and we know that identity function is a bijection. So we got the identity element. So we know that identity function we denote it by I from R into R is bijection. That is, this what we are saying is that identity function belongs to SR, and we know that the property of identity function is that when we compose it with any other function, we get the same function. And we know that if we compose a bijective function f with the identity function, or we compose identity function with a bijective function f, result is same, and that is function f. Therefore, I is identity element in SR. Therefore, identity function is identity in SR. Next we come to inverses. So number 4 about existence of inverses. So we know that every bijective function can be inverted. How we do that? Let me explain that. So let f from R onto R be a bijection. Let this be a bijective function. Then we define a function, we denote it by f inverse from R onto R by saying that effect of f inverse on x will be equal to y if and only if x is equal to fy. And you can see that this is exactly the inverse of the bijection. So that if we compose f with f inverse, or we compose f inverse with f, we will get identity function. And you are very much familiar about this particular function, f inverse, if f is a bijection. And you can very easily check this, that this is in fact inverse of the function f. So therefore SR is a group, because we have defined binary operation. We have seen that the binary operation is associative. We have seen that identity element exists. And we have seen that inverse of each element of SR exists in SR. So we define, let's just note that, let me put it as a note. I forgot to write it before. Note, if f is bijection, then f inverse is also bijection. That is, f inverse belongs to SR. In fact, I forgot to write it before, so I have just noted it at the end to complete our argument. And therefore SR is a group. SR is a group. So having done that, let's make an observation, or let's take a note. We note that for two bijections f and g belonging to SR, if we compose g with f, and then we compose F with G, they may not be equal. In general, composition of functions do not commute. Therefore, SR is non-abelian group. So this is very important, non-abelian group. So if you're given a set, let's say set A, then SA, the set of all bijections from A onto A is a group, and this is a non-abelian group. So having said that, let's come to a very particular example. Let's write it as a definition. We have proved a general result that if we are given a set A, we have taken, in fact, set of real numbers R, we could have taken some other set A, then the set of all bijections from A onto A is a group, which is a non-abelian group. Now, we can take a finite set, then the set of all bijections from that finite set onto that finite set will also be a group. And note that bijections from a finite set, non-empty finite set, I must say that, bijections on a finite set or bijections from a finite set onto itself is called permutation. So what I am going to define is, this is definition of permutation. So the definition is that a bijection from a non-empty, a bijection from a non-empty finite set onto itself, non-empty finite set, note that finite set. So a bijection from a non-empty finite set onto itself is called a permutation. We will discuss this concept in much more detail, but I have written this definition just here because I want to write corollary of our above proposition, that the set of all permutation on a finite set is a group. The set of all permutations on a finite set. Permutation is in effect bijection on a finite set. It is just to be careful. The set of all permutations on a finite set is a group. In fact, non-abelian group. And the reason is very simple, because the set of all bijections from a set A onto itself is a group which is non-abelian. So if you take this set A as a finite set, then the set of all bijections, which we now call permutations, is also going to be a group, and of course a non-abelian group. So let's come to a concept called permutation. Permutation. Let me give the formal definition first, then we'll discuss that. तो डेफिनेशन ये है कि a bijection of a finite set, a bijection one-to-one mapping, a bijection of a finite set finite set, let's have that set as S is equal to 1, 2, 3, so on up to n, finite set. So a bijection of a finite set 1, 2, 3, 4, so on up to n onto itself is called a permutation. So a bijection of a finite set onto itself is called a permutation. Having defined that, let's see an example. हम सेट S ले लेते हैं. लेट S इज इक्वल टू, छोटा सेट लेते हैं ताकि हम आसानी से चीज़ों को लिख सकें. 1, 2 and 3. हम 1, 2, 3 से लेकर 1, 2, 3 तक ऑल पॉसिबल बाइजेक्शंस 1 to 1 और ऑन टू मैपिंग्स हम कंसिडर करते हैं. अब ये सबसे पहली मैपिंग तो यही है कि आप 1, 2, 3 और ये 1, 2, 3 है. आप 1 को 1 पर मैप कर दें, 2 को 2 पर मैप कर दें और 3 को 3 पर मैप कर दें. दिस 1 to 1 ऑन टू मैपिंग. एक पॉसिबिलिटी ये है कि आपके पास 1, 2, 3 है और इसे हमने 1, 2, 3 पर मैप करना है. तो आप यूँ करें कि आप 2 को 3 पर मैप कर दें और 3 को 2 पर मैप कर दें और 1 को 1 पर मैप कर दें. ये दूसरी पॉसिबिलिटी है. तीसरी पॉसिबिलिटी ये है कि आपके पास 1, 2, 3 ये गिवन सेट है, यही डोमेन में है, यही रेंज में है या को डोमेन में है. तो आप यूँ करें कि 1 को 3 पे मैप कर दें, 3 को 1 पे मैप कर दें और 2 को 2 पे मैप कर दें. एक ये पॉसिबिलिटी है. एक पॉसिबिलिटी ये है कि 1, 2, 3 और 1, 2, 3 यही को डोमेन है. तो आप 1 को 2 पे मैप कर दें, 2 को 1 पे मैप कर दें और 3 को 3 पे मैप कर दें. एक पॉसिबिलिटी ये है कि आप पास ये डोमेन 1, 2, 3 है, को डोमेन या इस केस में रेंज भी यही है 1, 2, 3 है. तो आप इसमें आप 1 को 3 पे मैप कर दें, 2 को 1 पे मैप कर दें, 1 को 3 पे मैप कर दें, 2 को 1 पे मैप कर दें और 3 को 2 पे मैप कर दें. और एक पॉसिबिलिटी ये है कि आप पास डोमेन 1, 2, 3 है, को डोमेन भी 1, 2, 3 है. तो आप यूँ करें कि 1 को 2 पे मैप कर दें, 3 को 1 पे मैप कर दें और 2 को 3 पे मैप कर दें. यही पॉसिबिलिटी रह जाती है ना, 2 को 3 पे मैप कर दें. अब देखिए, आप कोशिश करें, इसके अलावा कोई और पॉसिबिलिटी नहीं है. यू कैन ट्राई इट बाय योरसेल्फ. इसके अलावा कोई पॉसिबिलिटी नहीं है. इसे आप जानते हैं, ये आइडेंटिटी परमुटेशन है. इसे हम आई कह लेते हैं. इसका आप कुछ भी नाम रख दें, FGH रख दें, लेकिन मैं इसे अल्फ़ा कहने लगा हूँ. उसकी वजह यह है कि इसे फिर हम बीटा कह लेंगे, इसे हम गैमा कह लेंगे, इसे हम डेल्टा कह लेंगे और इसे हम म्यू कह लेते हैं. अगर हम एफ जी एच लिखते तो फिर एफ जी एच आई जे के थोड़ी सी ज़रा कन्फ्यूजन सी हो जाती। तो हम इसका नाम आइडेंटिटी परमुटेशन है। इसे आई कह लीजिए, इसे अल्फ़ा कह लीजिए, इसे बीटा कह लीजिए, इसे गैमा कह लीजिए, इसे डेल्टा कह लीजिए, इसे म्यू कह लीजिए। हम इन्हीं परमुटेशन को हम इस तरीके से भी लिख सकते हैं, वी मे राइट these permutations as follows. बस हम ये कर सकते हैं कि ये जो आइडेंटिटी परमुटेशन है, आइडेंटिटी परमुटेशन को हम लिख सकते हैं 1 2 3, 1 goes to 1, 2 goes to 2, 3 goes to 3। ये जो अल्फ़ा परमुटेशन है इसको हम लिख सकते हैं 1 2 3 और 1 goes to 1, 2 goes to 3, 3 goes to 2। ये जो बीटा परमुटेशन है इसको हम लिख सकते हैं 1 2 3 and 1 goes to 3, 3 goes to 1 and 2 goes to 2। एंड ये जो गैमा परमुटेशन है इसे हम लिख सकते हैं 1 2 3, 1 goes to 2, 2 goes to 1 and 3 goes to 3। और ये जो म्यू परमुटेशन है वी कैन राइट इट 1 2 3, 1 goes to 2, 2 goes to 3, 3 goes to 1। So these are the permutations on 3 elements, 1 2 3, a set of 3 elements. These are the all permutations. Note that 1 2 3 4 5, 1 2 3 4 5 6, 1 2 3 4 5, we have written identity permutation, we have written alpha, we have written beta, we have not written gamma। 1 goes to 2, 2 we have written gamma, we have written delta, and let me write delta as well, and delta is equal to 1 2 3, 1 goes to 3, 2 goes to 1, 3 goes to 2। मैं इसे भूल गया था लिखने में। तो 1 goes to 3, 2 goes to 1 and 3 goes to 2। तो ये so these are 1 2 3 4 5 and 6 permutations on 6 elements। So there are 6 permutations on a set of 3 elements, and recall that from your intermediate 3 factorial is equal to 6 as well, and you have studied a chapter on permutation in your intermediate, and from there you can recall that, we further recall that for n greater than or equal to 1 number of permutations on set S which has got n elements, 1 2 3 so on up to n। Number of permutation on S is n factorial, as set S has 3 elements, so there are 6 permutation, 3 factorial is equal to 6। Let's write an example. Let S is equal to 1, 2, 3, 4, then number of elements, then number of permutations. On S or off S, whatever you like, is 4 factorial, and this is equal to 24. So number of permutations on 4 elements is equal to 24. 4 into 3, 12 into 2, 24. And similarly, number of permutations on 5 elements, on 6 elements, and so on. Let's talk about notation. Let's take first example. Let S is equal to 1, 2, 3. Now permutations on S we have seen. These are the permutations on according to our notation. So identity permutation, then we denoted by alpha, one other permutation, then beta, then gamma, then identity alpha, beta, gamma, delta, and mu. So these were the 1, 2, 3, 4, 5, 6 permutations on this set S, where I, alpha, beta, gamma, delta, mu, the symbols stand for permutations already described. We write this set of permutations as S3. S3. Number of set of permutations on 3 elements. Similarly, S4 stands for the set of permutations on 4 elements. And in general, Sn stands for the set of permutations on n elements. Let me note few things along with. And we have noted that number of elements in S3 is equal to 3 factorial, and this is equal to 6. Number of elements in the set of permutations on 4 elements is equal to 4 factorial, and this is equal to 24. And the number of elements in the set of permutations on n elements is equal to n factorial. So these are quite important results. Let's move further. Note that if we are given two permutations, we can compose those two permutations with each other, and the method is same as we have composed symmetries of a square and symmetries of a regular pentagon. And in fact, this composition is same as composition of functions. We can discuss this as well at later stage, but let's get benefit of our experience over working on compositions of symmetries of a square and symmetries of a regular pentagon. So composition of permutations. Composition of permutations. Let me just comment that this is same composition as is the composition of function, but we will discuss that at some stage. The simplest example is consider S3, and we know what S3 is: identity permutation, alpha permutation, beta permutation, gamma permutation, delta permutation, and mu permutation. And what does this mean? We already know. First of all, note that if we compose identity permutation with any other permutation, suppose alpha, identity permutation is 1, 2, 3, 1, 2, 3, and alpha permutation is 1, 2, 3, and 1, 3, 2. 1, 3, 2. So let's compose these with each other. This will be 1, 2, 3. 1 goes to 1, 1 goes to 1, so 1 goes to 1. 2 goes to 3, 3 goes to 3, so 2 goes to 1 goes to 1, 1 goes to 1, so 1 goes to 1. 2 goes to 3, and 3 goes to 3, so 2 goes to 3. And then again 3 goes to 2, 2 goes to 2, so 3 goes to 2. So note that this is same permutation, this is alpha again, and you can check that if we compose alpha with identity permutation, this will be alpha again, and therefore identity composed with alpha is equal to alpha composed with identity is equal to alpha. In fact, this identity composition plays the role of identity element. Similarly, you can check with other elements. You can check with other elements of S3. Let me say it, other elements of S3. So what we conclude is that identity permutation is identity element in S3. Let me remark that the binary operation in S3 is composition of permutations. So under this binary operation, identity element is identity element. Plays the role of identity element. I composed with any permutation results in the same permutation. So we can compose any two permutations. Let's say, let me choose any two permutations. Let's compose beta with gamma. So consider we compose beta with gamma, and this is equal to beta is 1, 2, 3. Let me say see beta 2, 3, 1. And let's compose it with gamma 1, 2, 3, and gamma is 2, 1, 3. 2, 1, 3. So let's compose these two with each other. So 1, 2, 3, and you can see that 1 goes to 2, 2 goes to 3, so 1 goes to 3. 2 goes to 1, 1 goes to 2, so 2 goes to 2. 3 goes to 3 and 3 goes to 1, so 3 goes to 1. And you can see that this permutation 3, 2, 1 3, 2, 1. This permutation is beta is 2, 3, 1 composed with 1, 2, 2, 1, 3, 3. 1 goes to 2, 2 goes to 3, 1 goes to 3, 2 goes to 1, 1 goes to 2, 2 goes to 2, 3 goes to 3, 3 goes to 1, so 3 goes to 1. So this is 3, 2, 1, and 3, 2, 1 permutation is just let me correct that. In fact, what we are composing is beta 2, 3, 1. In fact, this is mu. Let me correct it. So मैं दूर से देख रहा था, मुझे वो नज़र नहीं आया था. This is mu. So mu composed with gamma. So mu is 2, 3, 1, and then gamma 2, 1, 3. And result is 3, 2, 1. This is beta. इसमें थोड़ी सी मुझसे लिखने में गलती हुई, इसे नोट कर लीजिए. तो we composed mu with gamma and result is equal to beta. And let's compose gamma with mu. Gamma mu. So gamma is 1, 2, 3. 2, 1, 3, and let's compose it with mu. 1, 2, 3. Mu is 2, 3, 1. 2, 3, 1, and this is equal to 1, 2, 3. 1 goes to 2, 2 goes to 1, so 1 goes to 1. 2 goes to 3, 3 goes to 3, so 2 goes to 3. And 3 goes to 1, and 1 goes to 2, so 3 goes to 2. And this permutation is equal to 1, 3, 2. Let's see that. This 1, 3, this is alpha. 1, 3, 2. 1, 3, 2. This permutation is alpha. So when we compose mu with gamma, we get beta. And when we compose gamma with mu, we get alpha. So we know that mu composed with gamma and gamma composed with mu, these two are not equal. So our conclusion is we have to check that. Let S is equal to 1, 2, 3, then S3 is equal to, we have denoted these by I, alpha, beta, gamma, delta, and mu. Then S3 has a binary operation, that is composition of permutations, composition of permutations, where number one, S is closed under this binary operation. S is closed under this binary operation. You have to check it as assignment. I will make that assignment at the end. You have to check it. Secondly, identity permutation is identity element in S3. And then number 3, S3 is composition of permutations is not commutative in S3. Composition of permutations is not commutative in S3. Let's make me a comment. Since composition of functions is always associative and permutations are functions as well, therefore composition of permutations is also associative. Since composition of functions is associative, therefore the binary operation as we have defined, that is composition of permutations as we have defined, is associative. Think about definition of group. Note that only one thing is left, and that is inverses. Let me comment that in S3, inverse of every element exists under this particular binary operation, composition of permutations, and you have to check that by the help of table. I will develop the table for your assignment. So all we have left from the definition of a group is inverses. So all we have left from the definition of a group group is existence of inverses. Inverses in S3 under binary operation composition of permutation. And for this I give you the following assignment. For this you have following assignment. Complete this table. Complete the following table. So this is the table. Let me draw it with the help of ruler. सॉरी इसमें टाइम लग गया। मैं पहले एक टेबल मैंने बना के रख लिया था, इसे हम ज़रा आपने खुद बनाया। ये भी अच्छी बात, आपको अंदाज़ा हो टेबल कैसे बनाते हैं। सो आइडेंटिटी एलिमेंट, आइडेंटिटी परमुटेशन, देन अल्फा, बीटा, gamma, delta and mu. Same goes here. Identity permutation, alpha, beta, gamma, delta and mu. तरतीब एक जैसी हो, alpha, beta, gamma, delta, mu. Identity permutation will give you identity, alpha, बीटा, ये आपने मुकम्मल खुद करना है, ये भी सब. You have to complete this table, and having completed this table you will be able to see that each element of this set S3, set of permutations on 3 elements, has an inverse. You will be able to see that. So complete it as assignment. To complete the following table, after having done that, completed it, find inverses. You will be able to see the inverses. Find inverses. और आपको तरीका पता है इन्वर्सेस का। आप ये करते हैं कि जहाँ भी कहीं आइडेंटिटी एलिमेंट आता है, उस आइडेंटिटी एलिमेंट के इस तरफ एलिमेंट, उसके बिल्कुल टॉप वाला एलिमेंट एक दूसरे का इन्वर्स होते हैं. सो कंप्लीट इट एंड देन फाइंड द इन्वर्सेस.